So go ahead to the next slide. This is just an overview of some of the work that we do in our group because many times there will be criticisms of those who speak at conferences like this that they're not practicing scientists, that they read papers and they write books. But I write very few books. In fact, I've only written one book and I'll never do that again. And I've written chapters for books, but only at great urging. Usually I just publish papers. We publish papers in journals. That's what we do in my world. And so we work in a number of different areas. And the reason I'm telling you all this is because I want you to see that I really am a practicing scientist. I rarely attend conferences like this. I'm usually in conferences with scientists and engineers. But we work in an area called laser-induced graphene. That's where we can take, this is a polyimide sheet, and hit it with a laser and write patterns of graphene. Graphene is single sheets of graphite, one atom thick, and it's the strongest material known at that level. And generally it's made at high temperatures, and this is all done in the air with a laser. This is on bread. That's not dropping down ink. That is converting the carbohydrate atoms in the bread, molecules in the bread, these carbon atoms in that bread to graphene. So we convert that. That's a coconut we turn into a supercapacitor. So we can do it on food. You say, why would you want to write patterns on food? Well, why wouldn't you? So if you have, for example, a potato and you can just mark it very quickly, just as on every one of your plastic bottles, it's a water bottle, it has a little laser scribe date. If we can laser scribe electronics very quickly, you would know exactly what field that potato was picked from, what date it was picked on. And if you build in electronics, you can put an E. coli sensor, a salmonella sensor. You could build in electronics into food very rapidly. We split carbon nanotubes, and we use these in medicine, and we use these also in electronics and batteries. This is two-terminal memory. This has all gone commercial now. This is commercial memory now. Two-terminal memory. We work in the area of traumatic brain injury and stroke. There'll be a company launched this year for that, and also dementia. We work on supercapacitors. This is where we've taken asphalt and we can trap over 208% CO2 in it, and we use it for removing CO2 from natural gas. That's all licensed by Apache. This is the leg of a cockroach that we can turn into graphene. I wanted to take something of negative carbon value. What has negative value? What do you pay people to take away from you? That's carbon. I figured roaches. We've done it with dog feces. We can actually turn this into graphene. Now, just to give you an idea of why you would want to do this, we did this with Girl Scout cookies. If you calculate all the carbon in a box of Girl Scout cookies, which is $4, and you convert that into graphene, that graphene that you could convert just from one box of Girl Scout cookies would be worth $15 billion, which shows you that the value of a material is not in the atoms itself, it's in how those atoms are arranged. Just like if you take a person, what's the value of a human being? Just take away the spirit, just the physical entity, just of like a robot. What would be the value of a human robot? Now, if you take that entity and you cremate it, you get less than a penny of CO2 and water out. Same atoms, arranged differently, bring the change in value. A piece of coal, $60 a ton. Same atoms in diamond, which has very high value. They're just rearranged differently. This is where we take graphene and grow carbon nanotubes. This is a company that started, it's being built up right now just outside of Houston. It's for lithium batteries. We work a lot in these areas of cleaning up water. We work in these areas of nanomachines. If you click it once, this car will start to go. So you click the slide advance once. Oh yeah, that's not going to run. I forgot because it's been transferred. So, all right, that's okay. Just trust me. That moves across the surface. so this, what happens is this top part spins and it pushes the car along, and it spins at 3 million rotations per second and propels the car. These cars are so small we can part 50,000 of these across the diameter of a human hair. 50,000 of them. And they have little motors that are all light operated. And now what we're doing is we're taking these same motors that spin at 3 million rotations per second. We put on a peptide and that'll direct it to the surface of a cell. a cell of choice depending on the peptide addend we put there. And then we activate the motor and it spins at 3 million rotations per second. It drills right through and the cell is dead in 1 minute. It's just these drilling into cells. So we're looking at this. So if you'd advance to the next slide. So these are just transitions to companies in the past 5 years. Graphene quantum dots, that's commercial now. It's working in anti-counterfeiting platforms and also for frac water tracking, 2-terminal ultra-dense computer memory, lithium metal batteries, corrosion inhibitors are already on the market. We're working on spinal cord repair, peripheral nerve repair, optic nerve repair. We want to do the works of Jesus Christ. We want to make the lame walk and the blind see. We've already made the deaf hear. So we're trying to build technologies that can do this, and this is real. We do this type of thing. We can cut a spinal cord completely in half in a rat and fuse this back up so the rat within 3 weeks has a 19 out of 21. 21 is the highest mobility that can be achieved, so it can get to near perfect mobility within 3 weeks. So that's a company now that's going in Tel Aviv, Israel. Treatment of pancreatic cancer, that'll be in clinical trials within 1 year at MD Anderson Cancer Center. DNA sequencing, this is doing the entire human genome map, entire human genome, not just 23andMe, the entire genome for $100 in 1 hour. This opens it up now to everyone in the world. We work in this area of water purification based on laser-induced graphene. We have inserts for texting with long fingernails. So if you have long fingernails and it's hard to text, we got a little thing you just put it on your fingernails and you can text just fine. There's actually a big demand for that. I mean, this is real stuff. This is the traumatic brain injury, stroke, and dementia drug. A company will launch this year. Graphene synthesis at $100 per ton in energy cost, going to concrete, plastic, and metals. That'll launch this year. And then the molecular nanomachines to kill cells. That's going to cancer and the killing of superbugs. These things that are resistant to antibiotic resistance. We can drill right through them. And a friend of mine here, Richard, is here, and he works on this as well.